All right, guys, and we are back with Paper to Reality. And today we have a great question ahead of us, and it comes in at our university level category. And today this question is from Stacy, and she says, I'm in a university statics class right now, and I'm having a lot of trouble wrapping my head around how and why the angle that a force is applied at changes how powerful the force is. Please break that down for me. And of course, getting you clarity for that question is going to be absolutely no problem. Now, starting off, this is a statics question. And for everyone that has ever had the pleasure of never taking an engineering course, what is statics? Statics is the absolute crux of engineering, focusing on how forces interact within still, non-moving objects. Think ladders and buildings. Answering questions like how your favorite bridge can hold X amount of tons. First, we'll start off working up to your understanding of this problem with a simple diagram. Here we can see three different diagrams, A through C, showing three different force models. Now, looking at these three diagrams, we can see that they all have the same characteristics except for the angle that is between our imaginary x-axis here and the direction that this 100-Newton force is being pulled at. And no, not those newtons, these newtons. Why does this angle matter at all? This angle is called the angle of inclination, and depending on this value, the resulting force that is experienced at the point of contact, right here, will be greatly altered altogether. Now let me prove that real quick before I go forward. Okay, perfect. Now let me preface this. When forces are applied at non-perpendicular, aka 90-degree angles, that force must then be broken up into two categories, assuming we are in a strictly two-dimensional space, those being the amount of force applied in the x, the horizontal or like left-right directions, and that's going to be called the f of x value. And secondly, the amount of force being applied in the y, the vertical up-down direction, and that's going to be called the f of y value. And yes, I know, this sounds very bad at first, but trust me, it gets easier, it's not too bad. Now looking back at our example, if we think about these models having that 100-Newton force being broken into two x and y components, we can make a couple simple assumptions. Looking at model A, since the direction of the force, which is just simply the way the arrow is pointing here, is leaning more so in the horizontal or x direction, we can assume that it will have a greater force value in the x direction than that of the y direction for this model. And now looking at the math, this is true. So some of that logic can be applied to the C model now, where since the direction is more vertically inclined, it will be more likely to have a greater force value in the y direction than its x direction. All right, your brain hurt yet? Cool, mine did too. This stuff isn't easy. But we can step away from these annoying homework-type models and make everything a bit easier to understand now. And let's start off doing so by simply grasping an understanding on why the amount of force in whatever direction actually matters, and why it makes a difference at the end of the day here. My favorite experiment that really helped me grasp this stuff was actually a little mental physical engagement activity. And the best part of it is all you need for this is a spare wooden pencil that you really do not care about. All right, now let's kick this off. So all you have to do is grab the pencil at one end and hold it there very tight. Then, with your other hand at the opposite end of the pencil, you're going to try to break the pencil by following those previous diagrams we saw. And by that I mean through first applying a downward force at 30 degrees. Think about it like pulling the pencil with 2/3 of your force going outward and only 1/3 going downward. Did it break? Hopefully not. And if it didn't, use the same amount of force, then try it at a 45-degree angle and then a 60, and keep going all the way towards 90 degrees, where you would then be pulling straight downward at that 90-degree mark with no outward force whatsoever. Now, first of all, sorry about the loss of your pencil. But hopefully this little experiment helps you understand the following. The closer a force is to having a perpendicular, aka 90-degree angle of inclination, the greater the output of force will be on that object. As rather than the forces being split up between two different directions, the entirety of the force is isolated to only one direction. And in the case of the pencil here, that was the y direction, aka straight up and down. And hopefully through this experiment, you could have seen that the closer you got to that 90-degree mark on the pencil, the more and more force it felt like was being exerted on the pencil. And you might have seen this through it bending or hearing a cracking sound, but that explains the concept of split forces. So with that, hopefully this helped at least begin to understand why the value of the output forces changes with varying angles of inclination. Any engineering or statics course, especially those at a university level, are some of the hardest concepts to wrap your head around. But with enough patience and the knowledge to know when you need to take a step back and rethink any material, anyone can find a way to overcome any scholastic obstacle. And sometimes, all it really takes is taking any issue on paper and turning it into a reality. Thank you for watching. Have a great day, everyone. Take care.